All right, yet another video installment of BI458's Vertebrate Biodiversity and Conservation class. It turns out I've been way too overambitious, and I thought I could cover both patterns of biodiversity and extinction in one lecture. And that just hasn't worked. So in class, we were able to get through all of patterns. Now we're going to get into extinction. I know we talked a little bit about extinction at the end of the class, but I figured let's just start from the beginning with extinctions. We'll go through all of the slides together, and it'll stand alone, I hope. So let's get into it. We had a great conversation about what's worse, losing genetic diversity, species diversity, or what I put here is ecological diversity, and what I really meant was community diversity, and why. And the class had some really great and insightful comments. The class mostly felt that preserving genetic diversity was important, although there was certainly some support for preserving ecological diversity. However, E.O. Wilson, who's certainly one of the leading advocates for conservation today, argued that the extinction of species is the most serious aspect of environmental damage. And he proposed that protecting species as the functional unit of conservation is the most effective way of doing conservation. So his argument essentially was that by preserving species, you preserve, sorry, I'm going to say that again. By preserving species, you preserve the ability to restore ecosystems that have been damaged. So if you have local extinctions of species, as long as they reside somewhere else, you can always repair that ecosystem later. Right? So you got to have the species to do that. And then it goes the other way as well, that if you lose the species, the genetic diversity goes with them. If you have a small population, as long as you still have the species, over time, through processes like natural selection, they can regain that genetic diversity. So you have to protect the species. And one of the comments I liked from the class was that, how do you do this in practice? If you protect the community, you protect species, and by extension, you also protect the genetic diversity that they represent. So that's so I think where E.O. Wilson has philosophically a great argument, perhaps practically, for biggest bang for your buck, we focus on protecting communities first. Next, let's get into some definitions. What is extinction? And it's just basically when there isn't a single individual of that species left in the world. And we've got some current examples. If we just focus on birds, in Canada, we've already lost the Carolina parakeet, the passenger pigeon, and the great auk. So extinctions have been happening, and we've documented it. We've seen the very last individual of those species. The other type of extinction that we often discuss in conservation is when something is extinct in the wild, and that's when there are individuals that still persist, often in captivity or in cultivation, but in the wild, they're gone. There's some scale to consider when you discuss extinction. You can have something that's globally extinct, which means it's gone everywhere, forever. But you also can have regional extinction or extirpation. And we had wolves in Waterloo 100 years ago, but we extirpated them. We shot them and poisoned them and blew up their dens and killed their puppies and made them go away forever. At least, well, I shouldn't say forever. We've made them go away from Waterloo. But that doesn't mean that they can't come back. They can't be reintroduced or come back naturally. And then the other type of functional extinction that I want you to be aware of, and I think we're going to come back to this term several times throughout the rest of the course, is functional extinction. And that's when a population is so small that the species no longer has an appreciable effect on other species in its community. The function, the job that it served in that ecosystem is gone. And if that's a keystone species, even though that keystone species might still exist, if it's not doing its job, the rest of the ecosystem suffers. So a good example of this would be tigers. Tiger populations have been reduced to the point where, as a predator, they're no longer influencing competition or suppressing populations, so they're functionally extinct. This idea of extinction has been around for a while. It was identified in the late 1770s, and a guy named G.G. Simpson estimated that at this point 99% of all the species that have ever existed are extinct, which is a pretty big statement. And it makes sense because from the fossil record, there's lots and lots of organisms that are gone. And we've seen some pretty large natural mass extinction events. The only problem with this estimate is that we don't even know how many species we currently have, let alone how many might have existed previously. So it's a pretty bold statement, and it's really hard to verify. So that's the introduction to extinction. Let's get into some natural mass extinctions. But extinction happens naturally. There's been some pretty major extinction events. There's one at the end of the Ordovician, the Devonian, the Permian, the Triassic, and the Cretaceous. And these mass extinction events happen for all kinds of reasons. Global climate change, either cooling or warming, asteroid impacts, volcanoes, continental drift, changes in ocean pH, changes in oxygen level and temperature, and so on. Lots of good reasons for mass extinction events. The biggest one, the most important one, probably happened in the Permian. The other thing to take from this graphic, this figure, is that biodiversity has been increasing. In the last 40,000 years, we peaked. The world has never had as much biodiversity as it has had in the last 40,000 years. Now we're getting into what's called the anthropogenic mass extinction event. This is where we've seen a very recent decline in biodiversity. In fact, it looks like biodiversity peaked about 30,000 years ago, and it's starting to go down. It's not been just like a 20th century issue. And if you look at the expansion of the human species out of Africa into naive environments like the Americas, like Australia, like Madagascar, pretty much immediately after the introduction of humans, biodiversity goes down, and largely the large-bodied organisms go away really quick. And this is probably because of hunting and habitat alteration. Now, we sit in this interesting position where we have documented or observed extinctions, and about 1,000 species since 1600 have gone extinct. Of those, a fairly small number were vertebrates. 77 species of mammal and 129 species of bird have gone extinct since 1600. That's just a little over 3% in 300 or 400 years. That kind of sounds small, and I think lots of people take issue with the idea that humans are having this huge impact on nature, and we're in this mass extinction event when you see numbers like that. And yet you hear someone saying, well, we've named 2 million species. And only 200 vertebrates have actually gone extinct. It seems inflammatory. So let's dig into this a wee bit more, a little deeper. One of the biggest reasons to be concerned is that the rate of extinction is increasing. And not only is it increasing, where it used to be increasing mostly on islands, recently we've also been seeing an increase in extinction on continents. So there's two very worrisome trends there. There's this like downward trend at the end of this graph for this figure, and it's probably because we're a lot more reluctant to classify something as extinct. Conservationists, ecologists have been sort of caught their pants down more than once where we said, oh yeah, no, it's gone, it's extinct. And then 20 years later, somebody finds a population existing in some remote habitat somewhere. So biologists and conservationists have just learned to be a little more careful about classifying something as extinct. Now, another thing to consider is the comparison of what the current extinction rate compared to background extinction rates. And let's just work the numbers out. First, if you can figure out the average, how long species survive, you can make an estimate about what the background extinction rates are. So we use the fossil record for that. Marine invertebrates typically survive in the fossil record for about 30 million years. Mammals, about 2 to 3 million years. So let's take an average of this and say the average species persists for 4 to 10 million years. When you put that with current biodiversity estimates, which we've named about 2 million species, but best guesses suggest that we actually have about 10 million species that share this planet with us. When you put those two numbers together, you can calculate background extinction rates. And it looks like normally we'd lose 1 to 10 species per year, right? Which would be about 0.001% per year. And if you compare that to what we've observed for current extinction rates, and you could call them anthropogenic extinction rates, it looks like we're losing about 0.01% of all species per year, which that's at least 100 times, if not 1,000 times, faster than background rates. So that is much more convincing in terms of, are we in a mass extinction event? I think the answer is yes. Now, you can also use island biogeography theory to make estimates about global population decline. If you look at this graph, species area relationships can be used to predict the number of species that can occupy a known area. And if a habitat is reduced in size, it will only be able to support the same number of species as an area of similar size. Now, to be fair, this is just a general rule. There's lots of qualifiers that can change the outcome of this. So from this curve, what we see is that species present in an area increases asymptotically to a maximum value. And the shape of this curve will be different for different regions and different habitats and different types of species. But typically what we see is that with a 50% reduction in area, so there's about a 10% reduction in species. Or If it was a 90% reduction in habitat, it would be a 50% loss of species, and so on. And we've seen this in Singapore over the last 180 years. 95% of the original forest was destroyed. So this model predicts that around 30% of the species should be lost. And when you look at the actual number of native bird species, from 1923 to 1998, about 32% of the native birds disappeared. So in 1989, Wilson used island biogeography theory to try and estimate actual extinction rates, global extinction rates. And he used tropical rainforests and their biodiversity as a surrogate of global biodiversity, just because so much of our biodiversity is found in the tropics. And given that deforestation rates are about 1% per year, he predicted that 0.2 to 0.3% of all species will be lost per year. Now that means, assuming that biodiversity is about 5 million species, so maybe a low estimate, that 10 to 15,000 species go extinct per year, or about 34 species a day. And this probably largely goes unnoticed because most of those species are invertebrates and as yet unknown to science. So we will never know that we lost them. Now, there are many other estimates out there that vary considerably from these numbers, but most estimates suggest that basically by 2050, extinctions worldwide could be as high as 35% in Africa, 20% in Asia, 15% in tropical America, and 10% elsewhere. Ultimately, tens of thousands, if not hundreds of thousands of species will go extinct by 2050 if we don't act to do something about it. Now, not all species are equally vulnerable. There are some traits, some characteristics that seem to make some species more vulnerable than others. So if you're a species that occupies a narrow geographic range, when that range is threatened by human activity, the whole population may be at risk. So if you're a fish species that only exists in a single watershed, or a bird species that's only restricted to a single island chain. Now, point two would be that if, as a species, you're only found in a few populations, if not a single population, you can be eliminated by chance alone. Several populations provide redundancy, a backup plan, so to speak. Point three would be small populations. If you have a small population, you have what's called the small population paradigm, and you're more likely to go extinct because of demographic change, environmental change, loss of genetic viability, and so on. Some species that naturally have small, very dispersed populations, like large predators, are particularly vulnerable for this reason. And then point four would be declining populations, and this is called the declining population paradigm, and trends tend to continue if left unchecked. So if we don't do anything about declining populations, they will continue to decline. And then point five is species that are harvested tend to be over-harvested. And I really like the expression, utility has often been the prelude to extinction. So if something's useful to us, we typically will take it. And if it's really valuable to us, we'll take it all. So those are basically the five most important characteristics that make species vulnerable to extinction. There are a couple other factors that are worth mentioning, though, although they're not always universal. There's exceptions to these. But if you're a large-bodied animal, you're more likely to go extinct. if you're a poor disperser, if you're a seasonal migrant, if you have small genetic diversity, if you have very specialized niche requirements, if you require stable or pristine environments, if you're a species that groups together and you have dependent relationships, if your population is naive of people, you don't know that they're scary and bad and might want to hurt you, or if you have a dependent relationship and you've been abandoned due to other extinctions. Those are all characteristics that will contribute to your vulnerability risk. Endemic species often check many of those boxes. So an endemic species is a species that's found naturally only in a single geographic area and no other place. They have a single population. Often they're found on islands, but they can also be found on individual mountains or isolated lakes that are often of limited size. So they have a narrow geographic range as well. These species often have small populations and all the risks that go with a small populations paradigm. And great examples of endemism can be found in Madagascar, Australia, and Hawaii. Now, the International Union for the Conservation of Nature has really set the standard for ranking the risk of species to extinction. And they've got 9 categories that identify this risk. And it goes from extinct, which we've already discussed, to extinct in the wild, to critically endangered, vulnerable, near threatened, least concerned, data deficient, and not evaluated. And it's a hierarchical relationship, and basically of escalating conservation risk. So here are basically the way it works out. So when the IUCN is ranking risk, they have to have one of these 5 pieces of information, and then they have to compare that information to a threshold value given by the IUCN's Red List criteria as defined in 2001. So a species has to have observable reduction in numbers of individuals, so shrinking populations. They have to have a total geographic area that's occupied by the species. They have to know where they live. The scientists need to be able to predict the decline in number of individuals. They need to know the number of mature individuals that are alive, and if they can, they need to be able to determine the extinction probability in a certain number of years. They don't need all 5 of those, they need 1, but they need to do that one well, obviously. So here's an example. For a species to be listed as critically endangered, there needs to be a population that's declined by more than 80% in the last 10 years or 3 generations. Or if it hasn't happened already, it needs to be expected to do so for good reason. The species needs to have a restricted range of less than 100 square kilometers or exist only in one location. It has to have observed habitat loss or ecological imbalance or commercial exploitation. And it's important to note that they've included habitat loss in this one of these criteria for critically endangered species, because sometimes these species are really rare and we don't know a whole lot about them, but we know where they live, and we know that where they live is going away. So we can use that as a criteria to list something as critically endangered. We can also use the criteria that the population has less than 250 mature breeding individuals, and that's expected to decline by 25% in 3 years. Or if someone's gone to the trouble of doing an extinction probability analysis, that needs to be greater than 50% in 10 years. And what's great about the IUCN's ranking criteria is that it's science-based, and it's quantifiable, and it's comparable, so it can be evaluated by other scientists. But the major disadvantage is that it's time-consuming and expensive, which is actually a pretty big deal because most of the world's biodiversity exists in developing countries and in areas that are rapidly changing. And so we need, one of the things the first world can do to support the developing world is fund projects and institutions that are actively trying to rank the risk of their species. Now, in Canada, we've taken the same approach. We use basically the same criteria, and we use the same categories to rank the risk of our species. In Canada, this work is largely done by COSAWIC, the Committee on the Status of Endangered Wildlife in Canada. There's also an Ontario branch, so drilling down here to like a more local example. In Ontario, we have COSERO, which is the Committee on the Status of Species at Risk in Ontario. And they each use the same IUCN ranking criteria, but they also include the category extirpated because they're considering regional losses as well. So, in summary, extinction. We know extinctions have happened before. We know human activity has caused a large loss of biodiversity, and we're in what might be called the sixth mass extinction. Functional extinction impairs ecological services, and this might be as bad as actual extinctions. Not all species are equally vulnerable, at risk, or important even if you consider keystone species. And then the rate of species population shrinks sets its conservation status. All right, I'm going to leave it at that. Thank you everybody for listening. I'm sorry there weren't more pictures in this one. We'll see if we can't spice up the next lecture a little bit. If you have any questions or comments, please let me know. And you can just email me directly at lmoore@wlu.ca. Thanks and bye for now.